Welcome to the summary of an empirical study on the design and evolution of NoSQL database schemas. My name is Stefanie Scherzinger from the University of Passau, and I'm presenting joint work with Sebastia and Sidortschuck, a former student of mine and now a developer at SpareTech.io. The motivation for our case study is the following. There are various empirical studies on schema evolution in relational database management systems, but when it comes to NoSQL data stores, we mainly rely on anecdotal evidence or focus on a single application. So we're missing systematic work on this. At the same time, the data is available since there are various open source projects on GitHub that use, for instance, MongoDB or Google Cloud Data Store. So this is the kind of application that we're looking at. We have a domain model. Again, in the online role-playing scenario, that would be a player. Each player has an ID, a name, credits, a list of missions. And this list of missions is a multi-valued attribute, so a collection of missions. Each mission, again, has an ID, a title, some difficulty, and whether the mission is completed or not. There are also class methods, but they are not schema relevant. So an object mapper such as Objectify persists player objects as entities in Google Cloud Data Store, and that's a physical entity here written down in JSON notation. So the class name becomes the kind. In MongoDB, we would be talking about the collection. Each player has an ID, a name, some credits, and an array of missions. And again, each mission has the kind mission, an ID, a title, a difficulty, and whether it's completed or not. Now we can analyze the Java code to find the entity class declarations, and looking at their attributes, we know what the physical entity is going to look like. There are some limitations to this analysis. Since it's a static analysis, if classes use Java generics, we cannot tell at compile time what the generics will really stand for. But apart from those small limitations, we can pretty much judge what the physical entity will look like. And when the code changes, we also know that the schema changes. So here's a change player class declaration. The attribute credits has been removed and renamed to coins. And these object mappers support renaming by an annotation called also load. So please also load the credits in a legacy entity and treat it as the coins. Last login has been added. The hours since last login have also been added compared to the legacy class declaration, but this annotation ignore flags it as a transient attribute. So the values of this attribute will not be saved or loaded. So we can ignore them. And there's still a list of mission remains the same. And any changes to the class methods we can safely ignore because they are not schema relevant. And this is what we did. We identified 10 projects like this on GitHub, 5 of them using the Objectify object mapper, 5 using Morphia object mapper, and we searched all of GitHub actually for those top 5 projects each that have the largest schema in terms of the number of entity classes in the schema. The projects are quite different. Some have many commits, some have just a few commits, some have a small schema with just about 30 entity classes, others go up to about 80, and also the lines of code vary. But considering the schema, they were the largest schemas, and then we posed some research questions on this data. So the first question we asked are those NoSQL schemas denormalized? So what we see here is for each project and each entity class in that project, we see a bubble, and the bubble is blue if we know that it's essentially in first normal form. So there's no nesting, there are no multi-valued attributes. Otherwise, we assume the entity class is denormalized, and you see that there's no single project where all the entity classes are in first normal form. So we see evidence that developers really do denormalize their schemas, some more than others, but they all do. An open question is the motivation. Is it because it's a good fit for their domain model? Do they enjoy not having so much impedance mismatch? Or are they forced to denormalize because the NoSQL data store doesn't has quite some restrictions on how you can specify integrity constraints, restrictions on the query language, join, or a very limited transaction system, so you need to denormalize and aggregate Otherwise, you can't have atomic updates on a player and all of his or her missions. Then we asked, what's the growth in complexity of the NoSQL schema over time? And in existing work on relational schema evolution, there are two very popular proxy metrics on the complexity of a schema, namely the number of tables and the number of columns. So here's a very nice paper by a group where they analyzed 10 open source projects with a relational database as its backend. That's the percentage of commits analyzed, that's the percentage of tables that have been created, and this line is the number of tables growing. You see that there's some refactoring phases, sometimes there are dips, but overall the number of tables keeps growing, and so does the number of attributes, that's the dashed line, so the schema keeps becoming more and more complex. We reenacted this study in our scenario, so the blue line, that's the number of entity classes, which you could compare to being similar to the number of tables. And you see that the number of entity classes keeps growing. The schemas are becoming more and more complex. There are refactoring dips where things change, but overall, it's a lot of growth. So we do see that we have similar dynamics as reported for relational schema evolution. The schema changes, the schema evolves, it gets more and more complex. One difference seems to be that in our setting, the schema takes longer to stabilize. And there is the share of commits where the schema is affected is higher, but at the same time, the projects analyzed by us are younger than projects in related work that are 10, maybe even 15 years old. So that's difficult to compare. They're not as mature in terms of age, understandably. A third question is, how does the schema evolve? What are the changes on the schema? And here we distinguish adding an entity class, and that in each project outweighs removing one. Adding a schema-relevant attribute, of course, outweighs removing a schema-relevant attribute because we saw a lot of growth there. And what I find interesting is that even though each project has a different distribution here, the last part, the changes to the schema-relevant attributes, is not that dominant. And that also contains type changes. And if you look at existing studies on relational schema evolution, the most frequent schema change is not creating a table or creating an attribute. Often it's changing the type of an attribute. And here we don't have so many type changes. I think the reason is that in our setting, for instance, for a string, you only have the Java string as a type, whereas a relational database management system offers you different versions of strings, chars, varchars, clops, and then the more types you get, of course, the more changes you're going to get. Choosing the right type is much more complex in the relational world. But that is just, that's my conjecture. I haven't performed a survey on that on developers. So to sum this up, even in schema-flexible or schema-free NoSQL data stores, there is the notion of a code-implied schema. Developers tend to denormalize this schema, whether by choice or by force is unclear to me. It's probably a mixture of both. And the schema evolves. Additions outweigh deletions. That's the same as in relational schema evolution. But the type changes do not play quite the same role as they do in many relational database management systems. With these observations, we now conclude our talk. Thank you for listening, and now we're ready to answer your questions.